are two types basically. Basically, two types are there. One is renewable energy generation, another is non-renewable energy generation. Now, the thrust is for renewable energy generation because the people have understood that the fuel that is what is available may hardly fossil fuels what we are using mostly for the generation of electricity may not last longer. Many people predict it may be hardly for another next 50 years or 70 years, whatever it is not going to be perennial. With that in mind, they are looking for many non-renewable energy generation. That means it should be perennial without affecting the environment, and it should be ever available. That type of concepts are catching up, and some of the cases I will be showing in the next this one. See, one is, as we have seen, wind. Using wind, we generate electricity, wind power. It rotates those fans and it is coupled to a generator. It generates electricity with all this control system, and lot of arrangements are there just to have this. This is the wind power. Next, what is seen here is the solar power. Photovoltaic cells, they are assembled in a parallel series combination and require the sunshine light falls on the solar cells, it generates electricity. There's another method of renewable type of energy generation. Third one, this is water based, that is hydroelectric station. Water is supposed to be renewable type because of the nature, again and again there may be rain, there will be rivers, running waters. Using that water, we are using for generation of electricity. By driving a turbine and coupled to a generator, we generate electricity. That is also supposed to be one variety of renewable energy generation. And the last one, tidal, not the last one of them, is the tidal. See, when the tides in the sea rise and fall, there is energy in it. Using that energy, can we rotate a turbine, some arrangement with which it is which is coupled to the generator, and thereby generating electricity? That is being explored many of the countries, and that is another method of renewable. It is going to be a perennial. Tides are always there. Using those tides, we can generate electricity. And this one is the beneath the earth surface, there will be a temperature. As you go down and down the earth, you will get higher temperature. Using that temperature, thereby generating the steam, running a turbine coupled to a generator, we can generate. This is called geothermal electricity. So these are all the few renewable energy sources. Then biogas, most of the things are in the market, but this tidal and geothermal are being explored in Western countries. They are also being used in the present day, but still in our country we are yet to get these things. Next, non-renewable. The first one is nuclear. Sorry. Yeah. Non-renewable, nuclear. See here, the basic concept of rotating a generator using a steam turbine remains same. But to generate the steam, the heat is generated using the nuclear fuel. Here it has its own plus and minus. Though they are inevitable, though we require them at the present juncture, the nuclear waste management and handling of these reactors, they have their own problems. But this is one of the methods. Uranium fuel is used and thereby electricity is generated. Next one is this our gas turbine power stations. Gas turbines are rotated using the gas, maybe natural gas or any type of gas. They can be this is burnt and it is used to run the turbines. Turbine is coupled to generator, and then generator generates electricity which is used. This is also non-renewable. This gas is not going to be continuously available in the world. The last one is the thermal power. Here mostly the coal is used. Thermal power stations are plenty in number because coal is basically pulverized and it is used, it is burned, and then the boiler, it heats the water, it generates steam, and steam turbines are coupled to the generator, thereby generating the electricity. These are all the few items, and in a lower capacity, in an industry, in a captive use, most of these things we use. engine driven generators, alternators, engine driven. Maybe for smaller capacity, it is okay. So in the when I say generation, so many levels of voltages are available. Generally in this country, the generated voltage will be 11 to 25. 11 means it will be 15.75. Basically, BHEL generators, for example, they are rated for 15.75 kV kilovolts. See, basically, normally we say it is 11 kV. Maybe in some cases it may be 25 kV. What is the limiting factor here, you may ask? Why we should limit it to only 11 kV? Why not higher? Maybe. Problem is the insulation, availability of the insulation. Higher the voltage, you must have insulation with higher dielectric strength. Our technology and what insulations are available at present in this country, this can be used only up to this level. Thereby, we will be generating most of the cases at 11 kV, and later on it will be stepped up. Why it should be stepped up? Why it should be transmitted in higher voltage? We will touch upon in as and when these topics come. So generally, finally, in the user level, in the domestic level, is maybe a single phase load between phase and neutral 230 volts, and for three phase loads, LT, that is 415 volts generally. In many of the industries, large industries, we have high voltage equipments also. When I say high voltage, it may be 3.3 kV, 6.6 kV, even 11 kV. Motors may be in the sugar mills, for example, that churning mill motors may be 6.6 kV rated. Most of the cement mills, in many places in process industries, we find very heavy capacity motors which are supplied with either 3.3, 6.6 or 11 kV motors. They are high voltage motors. Why we are using high voltage motors, I will explain. Why not only low voltage motor? I will explain when we talk about motors. Typical transmission system prevailing in the country is like this. If the generating station generates the voltage at a particular voltage level, later on to transmit it to a long distance, the voltage is stepped up. That is, the generating station transformers are used. We will be dealing with transformers, also principles of transformers. Here I am only explaining the whole concept of total generation, transmission, distribution, and utilization. First, when it is generated, soon after the generating station nearby, there will be a station with a transformer. It steps up. It can be up to any voltage. Minimum nowadays it is 220, 400 kV. In some cases even 765 kilovolts. It is transmitted very extra high tension, ultra high tension, UHV 765 kV. It is transmitted to a different distant places, different load centers. There it is again stepped down, maybe 400 kV, and 400 kV network will be there. It will be distributed in the surrounding area. Again, after 400, it stepped down to 220 kV, 220 kV to 110 kV. Maybe there may be consumers who are getting the supply at 220 kV and 110 kV in a large customers. For example, in Bangalore, if you see our wheel and axle plants or large public sector industries, HAL, BEL, they are all getting at high tension voltages. I am referring the cases in Bangalore since I am from Bangalore. That's all. Okay, they are getting at higher voltages. So MRPL, for example, in Bangalore, they are getting at the voltage 220 kV. So such large consumers are supplied with high tension, very extra high tension voltage. They are tapped at this level. Later on, it is stepped down to 110, 66, 33, depending on the factory or industry size. At different levels, voltage will be tapped. And finally, when it comes to small and mini industries, it will be at 11 kV. Different states have different rules, but here in Karnataka, if the connected load is beyond 50 kilowatts, you must get the power at 11 kV. Why it is so, I will explain in a later stage. So in different, basically electricity is a state subject. Different states will have different rules. If the connected load in an industry is 50 kilowatt and more, he has to get the power at 11 kV and then step it down to 415 and use it for his loads. And again 415, if you use phase and neutral, then it will be 230, which generally we use in domestic loads. This is the basic schematic description of the whole distribution system prevailing in the country. Now you see, I have just given a case here. See here, this is plus 3 volts. I have purposely shown here plus 3, plus 4. Both are plus, but one is 4 and one is 3. So this is less positive. This is more positive. This is less positive. This is more positive. When I say less positive, it is more negative. It is more negative. When it is more negative, the electrons will be attracted towards this positive. So electron flow will be in this direction. Electron flow will be in this direction. If both of them are equal, there will be no flow. There will be no flow at all. When there is a difference in charge level, then there will be a flow like this. Electron direction flow is in this direction. See here. Okay, here, see here. See, this is a battery. This is a lamp connected through a wire. See here, this is the positive. Normally, conventional current from positive to negative, you take it. But electrons from negative, they are attracted towards the positive. See, electrons are traveling like this through the load, going back, coming back to the positive. Through the load. Load is working now. So this is called electron flow, and this is the conventional current. Generally, in practice, we take the current flow direction as from positive to negative, whereas electrons flow from negative to positive. It is just like our going in a bus, looking at outside trees. Trees, we feel as if trees are traveling in the opposite direction. Similar principle here. So the conventional current, this I explained. Let me not take. See, this is the method. Now, what is the current? Now, anyway, we have seen charge gets shifted from one atom to another, another to a third one. Like this, charge gets shifted. This is actually flow of electrical charges, electrons. Sometimes in semiconductor technology, we say them as holes through a conductor, a circuit. Current is the how many charges are traveling per unit time. The unit for this is ampere, number of charged particles passing a point per unit time. So 1 ampere, the unit for charge is coulomb. So 1 coulomb per second, if the charge flows, shifts one point to other point at a rate of 1 coulomb per second. So how many electrons? That is also given there, 6 into 1019 electrons per second. Then we call it as ampere. So this is called current. This is the unit for current, ampere. The force to shift this electron from the orbit, that the force what we call, this is the voltage. So it is the voltage, because just imagine, to make water to flow in a pipe, you require a pump. Unless pump pumps it, water cannot flow. Similarly, the charge cannot be shifted. I told you already, to lift from the outermost orbit, to displace one electron, you require some force. That force, what we call, is voltage. Volts. Force which causes the dislodging of electrons from the orbit is called electromotive force. What does it mean? Motive force required, force required to move the electron. Force required to move the electrons. EMF, electromotive force. So also known as potential difference. I told you this movement can start if there is a difference in charge level or potential. Then we call it as a potential difference. The unit for EMF or this potential difference is the volts, V. We indicate it by V. And generally this force, what is the source of this force? We get it from battery, because due to chemical action, positive and negative charges are stored in a particular place. When we connect them through the external circuit, the chemical reaction reverses and current starts flowing. And next is the generator by electromagnetic induction process. I will explain in the next slides. So this is the volts. Volts, kilovolts, millivolts, there are different units, and volts is the unit for particular force, EMF or potential difference or pressure or force, or whatever word we use, the unit is volts. For ampere, the rate of charge flow, that is ampere. It is indicated by I. B is indicated by V in the diagram, whereas ampere is indicated by I. Why I? Why not A? Because it is called intensity. It's from a French word, they have borrowed it, and they in the drawing, in place of A for indicating the current, they are showing it I. V we show as V, whereas current we indicate it as I. Now, electromotive force can be made to move. This I have explained. See, now one or two more things here. The outermost layer, how many electrons are there? They are called free electrons. Sometimes valence electrons. Valency number of an atom is given by that particular number of electrons. These are also few informations for knowledge. This all I explained. Potential difference. This is the force tending to make electrons to drift along a conductor. Now, what is resistance? What is resistance? Well, maybe in electrical jargon, many people say resistance. See, what do you mean by resistance? Resistance is opposition. The simple meaning of resistance is opposition. Naturally, here it is the opposition to flow of current. Resistance means definition is opposition to flow of current. How this opposition comes? Conceptually, how you can, logically, how you can say there is an opposition. So just imagine, I explain, the electrons are moving from one atom to other atom to atom. See, so many electrons will be moving in a conductor at a particular time. When these electrons are moving, there may be friction between them. They may dash against each other, thereby their speed will be slowed down. Their speed will be slowed down. You can see any current flowing conductor gets heated up. There will be friction, there will be dashing, there will be collision. Because of all these things, their speed is reduced. When the speed is reduced, what do we say? It is opposition to travel, opposition to flow. That is why we say resistance. Resistance. So the property of a material which opposes the flow of electrons through the material, this is called resistance. Yeah, this is due to the collision. I explained this. Unit of resistance is ohms, OHMS, ohms. The symbol is also omega. I have shown here. This is the. See, one thing I want to tell here: the names of all these units. Some units, the names the V, W, or ohms. The names are from the scientists who brought out all these concepts. So all these things we are writing in capitals. When I write OHMS, O should be capital. When I say write volts, V should be capital. Because just to respect the person who invented these things, contributed for the invention of these things. That's all. Now, next is power. Most of the words what we use in the electrical technology, I am trying to cover here. What is power? When you say 40 watts bulb, 100 watts bulb, 500 watts bulb, what do you mean by that? That means it can do certain work like this. So much work it can do. 40 watts, so much light it will give. 100 watts bulb gives some better, much more light. So it is rate of doing work. Similarly, here power in electrical power P, it is indicated by P and the voltage into current, pressure into current. V is the voltage into current, VI. Its unit is watt. Kilowatts on the higher side, megawatts, kilowatts, and the lower sides again, milliwatts, whatever it is. So watt is the unit. V into I. What is energy? This is total work done. Most of our domestic houses, we have energy meter every month. The authorities come and take a reading, send us a bill. What does it mean? In a month, how much electricity we have consumed. So the energy is the total work done. So energy is power into time. What is the power? Watt. Time is hour, watt hour. So 1000 watt hour make 1 kilowatt hour or 1 unit of energy. Many of us in our domestic consumption, I have consumed 200 units of energy, 200 units electricity. Whatever we say, those units mean 1 kilowatt hour. 1 unit is 1 kilowatt hour. I have told so many parameters in electrical technology, and there this one I just sum up. Voltage, potential difference between the two charges, or electromotive force, unit is volt. Current, flow of electrons, ampere. Power is rate of doing work, watt. Energy, total work done, kilowatt hour. And resistance opposes the flow of current, it is ohm, and the symbol also I have been in the bracket. This is just summing of these things. Now, what are all the Instruments we are using as usual. For measurement of voltage we use voltmeter, for current we use ammeter, for resistance we use ohm meter, and power wattmeter, energy meter, and if can measure using 1 meter multiple parameters, nowadays most of you see multimeter. And if you want to measure the very high resistance of an insulation resistance of an insulation, then insulation tester, many of us call, we are more used to the name Megger. Megger is a company basically who manufacture insulation testers, but anyway in field we call them Megger. So insulation testers which measures very high resistance, and nowadays clip-on meters to measure the current when the circuit is alive. And apart from there, we have plenty of meters. For example, to measure the light, we have lux meter, frequency meter, phase sequence meters, like this, reactive power meters. So varieties of power factor meters. So many meters are used in practice, but most commonly in the field, in the maintenance field, we are using these type of meters. Now, we will just briefly discuss about the transformer. Why transformer is required first place? I told you the generating station, we generate largely, most of the cases is 11 kV, barring few cases of maybe around 15, 20, like that, whatever it is. We are generating at a particular voltage. To transfer a particular amount of power, maybe 10 megawatt power, to a city of Bangalore from a generating station. Megawatt or watts? Watts, V into I. Megawatts is V into I. So, if I send the power at 415 volts, what is the current in that 10 megawatt? If I send the current at, transmit it at 11 kV, what is the current? If I transmit it at 220 kV, what is the current? As the voltage level is increased, current level is decreased, because V into I is constant, 10 megawatt I told you. So V into I is constant. As the V goes up, current is reduced. So once the current is reduced, cross-sectional area is reduced, cost is reduced. And that is the reason why after generation, we step up the voltage. There is a generator station transformer, there they step up generally up to 220 kV. In barring a few cases, maybe 760, more or less 220 or 400 kV. 400 kV transmission lines are very common nowadays, 400 kV. So it is, thereby the conductor sizes are very minimal. So this process is called stepping up the voltage from 11 kV to 400 or 220, whatever. So large distance transmission takes place at the higher voltage, current is very small, then it is taken into a receiving station. There you can stepping down 400 to maybe 220, maybe 110, maybe 66, depending on your requirement, you can reduce it. Then finally, when you come to your roadside distribution transformers, where it feeds to domestic loads, that 11 kV to 450, 11 kV to 450. In 415 side, always sending end, the transformer, one is the receiving end, one is the sending end. Receiving end is primary, this is primary, this is the secondary. Primary is always in delta, because three-phase transformer, 3 windings are there, so they have to be connected either in star or delta. Generally, primary side is connected in delta, and the secondary side, sending end, from here transmission line starts. Here, this particular side is connected in star. Because in star connection, if any wire cuts and falls on the ground, how do you protect this transformer? There is a fault. 400 kV line falling on the ground. 400 kV, 0. 400 kV to 0. Ground is at 0 potential. Enormous fault current. Probably it may flow through the ground to the transformer. Transformer may be damaged. So in a star connected system, a star N, it is grounded. So once it falls down, immediately fault current flows through this and goes to neutral. There we can provide a relay and we can trip the transformer. The tripping speed of the transformer may be 1.5 cycle. 50 cycles I told you. 50 cycles per second means 1 cycle 0.2 second. So in such a speed, it isolates the fault and these equipments are protected. So this is why sending end, this is the sending end, generally star is. This is the construction. The yoke is required because I told you this is the coil. This is fed here. This is called primary. Primary side is fed here. This carries the current. There will be flux induced here. This flux will link this. If there is no core like this, the flux have to link through the air media of air here. Air is not a good conductor of flux. I am using conductor, a wrong word. It offers a opposition that is called reluctance. It is a reluctance. Permeance, reluctance, and MMF equal to volt electrical circuits. In magnetic circuits, MMF is EMF, permeance is conductance, and this particular reluctance is resistance. So by providing this, we are making a easy path for the flux to link the secondary. Mutual induction, voltage is induced, and this voltage, how much this voltage? Now there are 10 turns here. Here also 10 turns. Whatever E1 is there, equal voltage will be induced. Now instead of 10, I made it another 10, 20 turn, connect them serial. In this turn 10 also, same voltage is induced. Another 10 turns, there also again same voltage. When I connect them in series, 10 plus 10, 20 turns, double the voltage will be available in the secondary. I am stepping up from here to here. I am stepping up. When it comes to receiving station in large load centers, again transformers are this side winding turns will be less, this side winding will be more. It will be stepping down. So now you know the purpose of the transformer in a generating station, to step up the voltage, the level of transmission line voltage, so that line losses are reduced, current is reduced, conductor sizes are reduced, transmission cost is reduced. In the receiving station, after receiving, you are stepping up or stepping down suitable to the user level. So for stepping up and stepping down, you require a transformer. Now, how these motors work, at least let me just explain how this motor works. Let me explain just in briefly. Now see here, we are giving the supply to the stator terminal. Here stator terminal is there. We are connecting the supply here. This and rotating portion and stationary portion have no interconnection. This is independent, and this we are giving three-phase supply. When you give the three-phase supply in the winding, in this winding, current starts flowing. When the current starts flowing in the winding, as I told you already, there will be magnetic field produced around this every conductor. So inside here, you have this rotor portion. So those magnetic field of the stator cuts this conductor. That is alternating current, alternating magnetic field, cutting the conductor. A voltage is developed here. In every conductor, a EMF is induced. When the EMF is induced, they are shorted here on both sides, closed circuits. A current starts flowing in this. That is called rotor current. Now you see, a current carrying conductor is here, current carrying conductor is here, and here you have a flux, magnetic flux here. A current carrying conductor cutting the magnetic flux will experience a magnetic force. Naturally, what will happen? This will start, it will experience a this will experience a mechanical force, and this is mounted on a free bearing. It will start rotating. It is not as simple as that. There is a rotating magnetic field produced. There is a more theory behind it. Just for the sake of understanding, I've explained at this level to this extent, so that you can understand how a mechanical force, how a rotating force is produced in this particular rotor in a induction motor. So there is no connection. That is why we call it induction motor. Induction motor, induction, self-induction, mutual induction. This is mutual induction, more or less the principle of transformer. A primary, that is the stator winding. A secondary is the rotor winding, shorted. So the slip ring induction motor, instead of the bars here, one side is this have a regular winding and connected in star. Second, three free leads are connected to the slip rings, and these are taken outside through the brushes, and they are terminated through the resistors. Why this resistor? And stator winding is same, no change. See, these are all the slip rings. This is the rotating portion. It has a regular winding. Again, core, silicon steel stampings, then again slots on that winding, with wire winding, not bars like squirrel cage. And they are terminated in one end. Through these brushes outside, we are connecting the resistance. How to control the speed of the motor? speed of many of the applications require different speeds. How to control? The squirrel cage motor, squirrel cage induction motor speed control. Generally they are called constant speed motors. Now the speed is given by this formula, N is equal to 120 F by P. I have told you. There is a slip and other terminologies we are not covering here because of the paucity of time. Anyway, squirrel cage induction motors are supposed to be constant speed motors. They will run at particular constant speed. That is the reason why we say it's a constant speed, whatever it is. How to have a different speed from this motor? First thing, each winding will give, depending on the number of poles, as per this formula, depending on the number of poles, you can get different speeds. Have a motor at 2 pole with 50 cycle supply, you will get 3,000, 3,000, you will get 3,000. Have a motor at 4 pole, you will get 1,500. So, having multiple windings in a motor, but how many windings you can have? Maximum 3 windings, otherwise motor size will become huge. So practically 2-3 windings in some cases. For different poles they will be wound, will be housed in a motor. One method. So next is same winding have tapping from the middle, that is called delta double star. Once you are connecting 3 windings of the 3-phase motor in delta, you will get 1 speed. Second time you make it double star. Double star. The figure I am unable to show it here. Double star. In a double star connected motor, you will have a center tap from each phase. There will be 9 terminals in the motor. Start end of 3 and again 3. 6 plus 3. 9 terminals will be there. Connect them in double star mode. Then you will get another speed. So that's one. Now changing the frequency. In this formula, if you change the frequency, you will get different speed. But this is the principle of variable frequency drives. Of course, there are so many other aspects involved. When you change the frequency, sometimes the voltage may have to be changed. So to change the frequency, you should have a lot of electronic circuitry. First you must rectify it, then variable DC and frequency variable. Lot of processes there. So that is used in a variable frequency drives in the present day.